So the idea of KiloNeRF is, so first KiloNeRF is making NeRF more than 2000 times faster, which is very impressive. And the idea is to replace the heavy MLP from NeRF, even though it's a medium-sized MLP. But as we need to query it millions of times to produce an image, it makes the inference slow. And the idea of KiloNeRF is to replace those medium-sized MLP with a grid of tiny MLPs, which reduce the floating point operations of each query. We can compare them in this figure. This is the NeRF model, which has quite a few kiloflops. On the KiloNeRF architecture, which is tiny, is much fewer kiloflops. On this, the representative power of those MLPs is enough because they represent only a small region of space. So by the end of this video, these are the results we'll get. These are the results we'll get by the end of this video. Let's dive into the implementation. We will not implement training with distillation. So as is mentioned in the paper, sometimes the implementation can have some artifacts. So distillation can help, but in order to keep the implementation concise, we will not implement that, but still we'll have very good results. And there are also a few other components we'll not implement, but to get started, this is very good results. Okay, so we, as usual, we use PyTorch to implement the paper, also NumPy and Matplotlib, a few helper libraries, and we're also importing data loader from PyTorch again. So let's start by creating the KiloNeRF class. So n is the size of the of each side of the grid, of the voxel grid, where we will store the MLPs. And as usual with NeRF, we use positional encoding, and we have the maximum frequency for the position and the maximum frequency for the direction. And we also encode the scale of the scene. So basically, that means that this gives a scale for the size of this side. So basically, 3 means that this represents, for example, 3 meters. Okay, so now that we have the constructor, that we have the API of the constructor created, let's implement the constructor. So we can start by creating this grid of MLPs. So a naive way to do that would be to create a grid and then store in each cell MLP. So basically, you could use torch.nn.sequential and store n times n times n MLPs. But if you do that without custom QDAC kernels, it will be very difficult to query all of your networks in parallel. That means that, let's say you want to query the networks for 2 cells. Let's say that you want this cell on this cell, and you want to query the network in parallel. You cannot do that very easily with PyTorch. Of course, there are ways to do it. But in order to do that very easily, I've decided to implement the neural network myself rather than using nn.linear from PyTorch. So basically what I'm doing, I'm creating this grid, n times n times n grid, and then in each cell of the grid, I'm storing the weights and bias of the MLP. So basically just creating the MLP myself and using Xavier initialization. That's why it's important to understand everything that is going behind the function call we use, so that when needed you can use them and implement them yourself. Okay, and then we can store the few variable given in the constructor. Now we can implement the positional encoding. So this is very easy, a straightforward implementation from the equations. So we take the sine and the cosine of 2 to the power of j times x. It's often omitted in the papers, but usually we also keep x in the output of the positional encoding. Now we can move on to the forward pass. So first we initialize the color and the density to zeros. And we will update them for most of the values. For some of the values, we will not update them. We'll see that in the next lines of code. So basically, we compute a mask. So for all the position, so all the location given as input, we check if they are within the volume represented by KiloNeRF or no. If they are in the volume, we will compute the color and density of those points. If they are outside of the volume of this cube, we set the color and density to 0. So what we do with IDX, we compute the IDs, so basically the cells where the position is. For example, this could be position 0, 0, 0. So based on the on X, on the scale of the scene, we compute the indices of the cells. Then we can do the positional encoding. So instead of feeding X to the MLP, we will map X to a space that is higher dimensional, and this is what we do with the positional encoding. That will help to learn the high frequencies in the scene. Now we can move on to implementing the MLP. So this is a simple MLP, so very easy. WX plus B, but we need to fetch the weights on the bias at the appropriate cells. So based on IDX, we can take the MLPs in the appropriate cells. That's why I've implemented the weights directly myself, so that I can do that in parallel and fetch a lot of different MLPs at the same time, very efficiently, without using multiprocessing or without using custom CUDA kernels. And then for those points that are within the volume, so where the mask is true, I can return the color and density predicted by KiloNeRF. Now we can move on to the rendering part. So there is this compute accumulated transmittance function. As the name suggests, it will compute accumulated transmittance from the alpha values. A straightforward implementation of the equations from the paper. Now we can compute a function, a differentiable renderer, so it will render rays. So given the model that will predict the color and the densities, given the origins on the direction, we will predict the colors of those rays. And we take Hn and Hf, which are the near and far bounds, and also the number of bins that will be used to approximate the integral with a quadrature. Okay, the first thing to do is to sample points t along the rays, and then what we'll do for not sampling always the same t, which is deterministic, this line, the line is 76, then we use perturb sampling in order to add a bit of randomness and to sample so that in each batch we sample different points. I'm going very fast there. If you are interested and want to learn this in more detail, I have a dedicated course about NeRF that is more than 10 hours, and I will put the link in the description. Once we have the point t, we can compute position along the rays using the origin and the direction. Once those points are computed, so we have a number of bins points per rays. We can also expand the size of the ray direction so that it will have the same size as X, and we can feed both of them to the NeRF model. So once the ray direction is the same size as X, we can feed them to the MLP, do a resizing, and then once the color and density values have been computed, we can reshape them to the initial shape. And now we can compute the color from those values. So again, this is a straightforward implementation of the equation from the paper. We can compute alpha, then the weights from so the accumulated transmittance from alpha, and then we can do this weighted sum, so computing the quadrature that will give us the color of the rays. As we are working with synthetic data that have a white background, we can add this term to the color that will do white background regularization, and that will help with floaters and some artifacts due to the white background. Now we can move on to the training loop. So we are checking an NeRF model that will be a nn.module. We take an optimizer, so a PyTorch optimizer, potentially a scheduler, a data loader that will store our rays on our target pixel values, a device on which we'll train, obviously GPU, otherwise it will be just too slow, on the near and far planes, the number of epochs for which we'll train on the number of bins. So we iterate over each epochs in the we iterate over a number of epochs required. Then in the data loader we fetch the origin, the direction, and the ground truth pixel value. And now it will be very similar to a supervised learning loop. So first we make a prediction from using the rendering function on the NeRF model. And then we can compute the MSE loss between the predicted value and the ground truth value. So this is very similar to supervised learning. It's very important to make this function random race differentiable so that we can compute the gradients of the weights of the NeRF model. And then we can set back the gradient of the optimizer to 0. Otherwise, they will just accumulate with PyTorch. Once they are set back to 0, we can backpropagate to compute the gradients, and then do an optimizer step to update the weights of the weights. Okay. And now we can put, before putting all the pieces together, we can implement the testing function to render arrays once the neural network is trained. So again, we take the same parameters as or very similar parameters to the training loop. An important parameter here is the chunk size. So because an image is maybe, let's say an image that is 400 pixels by 400 pixels, that's already quite a few pixels. And for each of those pixels, I need to shoot rays in the scene and sample this number of bins many points per rays. That means that I need to query my MLPs, even though they're small. I need to query them. I need to query my KiloNeRF model millions of times to do a rendering for a single image, and that can usually it will not fit in my memory. So what we'll do, we'll render chunk of the image, chunk by chunk, a bit like batch size in when we do the training. Okay, so given the image index, so based on the image index, the image we want to render, we will fetch the origin and the direction of those rays from the training data, and then little by little we will render the pixel values, and then we will put them back together. So we will concatenate all the results, we will form back the image, and we will reshape it to the size of an image. And then we can plot the results. So yeah, we create a figure, we plot the results, and we save it in memory. And now finally we can put all the pieces together. So we set the device, which will be CUDA. We load the training and testing datasets. So for now, I've just encoded them in a PKL file. If you're interested, I can add. I will add on the GitHub Python script so that you know all those files were generated. But if you want to learn more about all this is all the ways are computed from the camera parameters, this is all explained in my course about NeRF in the description. So then we can compute the KiloNeRF model. So 16 is the size of the number of voxel per side. I think 16 was the parameter from the paper. And then we can create the optimizer, the scheduler, and we can launch the training loop. But first we need to create the data loader. So once we've computed created the data loader, we can send everything in the training loop for 16 epochs. So we'll iterate 16 times over the whole dataset, and then we can do the inference. So generating the 200 test views that were not seen during training. The results are the same as the one I've presented in the beginning of this video, and this is very fast. You can compare if you go to my previous videos about NeRF. This loop will be very, very fast in comparison to the other loop that were very slow. So I really hope this video was helpful to you, that you liked it. If it was, please leave the thumbs up, it really helps with this channel, and subscribe for more videos related to NeRF and to machine learning. And as a reminder, I have a course about NeRF if you are interested. Thank you.